Hello everyone, good evening. I am Anesh Ambekar, PMRF and PhD candidate from Aerospace Engineering ISC Bengaluru. I will be conducting today's live session on the course Solid Mechanics offered on NPTEL by Professor Ajit Kumar. The course has the code NOC 22ME70 and this week the will be covering some doubts and questions related to the content covered in week 7. So in week 7, Professor Ajit taught us about linear momentum balance in cylindrical coordinate system. So we first started off with what is a cylindrical coordinate system. Then we went on to calculate the tractions for a very small volume, for a very small cylindrical element. We looked at a strong assumption which rapidly simplifies our process, and using that we were able to calculate the linear momentum balance equations. From there on, we also looked at displacements, and using displacements, we were able to calculate our strain matrix. And we looked at different types of strains, specifically hoop strain and radial strain. And finally, we also came across the formulation stress strain relation for linear isotropic material when we are using cylindrical coordinate system. So we'll start with the first problem. The first problem asks which of the following statements is or are true. The first option is cylindrical coordinate system can be used only for cylindrical bodies. So is this true? Yeah, correct. So cylindrical coordinate system is a underlying coordinate system, right? It doesn't have anything to do with the body shape. We are not assuming a body shape. So in general, it can be applied for any arbitrarily shaped body. Okay, so out of the options, only the third option, which is cylindrical coordinate system, can be used for bodies having arbitrary shape, is the only one which is true. Problem 2. Again, it is a true or false statement. Basis vectors ER and E theta in the cylindrical coordinate system are always perpendicular to each other. The third basis vector Ez is aligned along the axis and need not be perpendicular to the other two basis vectors. So,
False.
yeah, correct. So, we have, suppose you have this point, suppose you have this point. So, you can have this as ER, this as E theta, and Ez will always be perpendicular to the ER E theta plane. So, we always have ER dot E theta is equal to 0, Ez dot E theta is equal to 0, and ER dot Ez is also equal to 0. So E theta and Ez are perpendicular, are right-handed perpendicular coordinate basis. So this statement is obviously false. Problem number 3. Which of the following statements are true regarding partial derivatives of basis vector? Let's look at the first option. So the first option says partial derivatives of basis vector ER and EZ with respect to R and Z are always 0. So the first option essentially is dou ER by dou R and dou EZ by dou Z. These are both 0. This is what the first option is saying. If we remember our coordinate system, this is your ER, this is your E theta, and the one coming out of the plane is EZ. So we note that ER is a function of theta only. E theta is also a function of theta, whereas Ez is not a function of r theta or z. Ez is essentially a constant here. So therefore we have, using this we have dou ER by dou r is equal to 0. Dou Ez by dou r is equal to dou Ez by dou theta is equal to dou Ez by dou z. These all three are 0. Similarly for ER, dou ER by dou r is 0 and dou ER by dou z is also 0. Whereas for theta, dou E theta by dou r is equal to dou E theta by dou z. These two are 0. And if you remember, dou ER by dou theta is nothing but, is it E theta or minus E theta?
E theta.
Yes, correct. And dou E theta with respect to dou theta is minus ER.
Minus ER.
Yes, correct. So the first option says dou ER by dou R is 0 and dou EZ by dou Z is 0. Both of these are here. So first option is true. The second option says dou ER by dou R is 0 and dou E theta by dou theta is 0. Dou ER by dou R is 0, but dou E theta by dou theta is not 0. It's, as we mentioned, it should be equal to minus ER. So the second one is false. The third one is dou Z by dou Z is 0. So this statement is true, and the second part of the statement is dou E theta by dou theta is 0. Again, this is false. So first statement is true and true. It's nothing but true. Second is true and false is false. And the third statement is also true and false, which is false. So the third statement is also false. Only the first one is a true statement. Problem number 4. The approximate method, where we assume that traction does not vary over the planes, gives us the same linear momentum balance relations as the original analysis for the cylindrical coordinate system. Why does this happen? So this is, say, your cylindrical element.
Sir, actually traction varies.
Actually traction varies, but uh, in the second part, so I think it should be lecture 18, I think. In lecture 18, we make this assumption. So, do you remember the angular momentum balance relation when we were deriving? We also use this strong assumption where we said that whatever force, whatever traction rather acts at the center of a face, since the face is very small, whatever traction that acts on the face will take that to be the traction on any other point on the face. Right?
Yes, sir. Yes, sir.
So in both cases we were getting the same result, and the reason is same as what we are seeing here. So even if you have, say, some traction, suppose this is the traction on Z plus face, this is the traction that you are getting at the center of the Z plus plane. So even if we say, even if we apply the strong assumption that this traction does not vary on the whole of the plane, then we see that the overall result that we'll have. So wait, let me write it this way. So if we have no assumption, okay, in case of no assumption, face along say plus force along plus z is T center of plus z. So C plus C comma plus z. Center point of plus z times area into, sorry, one second. Let me rewrite this in a different manner. Right. So this is our cylindrical element, and if we use the strong assumption, it basically says that traction at any point on, say, the plus, I'm taking the plus z phase for as an example. The coordinates of the plus z phase would be, say, r theta r plus epsilon theta plus eta and z plus delta z by 2. Right, this is nothing but equal to t of plus z of r theta z plus delta z by 2. So when we calculate the force under the strong assumption, it is nothing but fraction of z dA on area of plus z. It's nothing but, I think this is what we get, right? If we choose the case of no assumption, right, then your traction on the plus z phase is traction at r plus epsilon theta plus eta z plus delta z by 2, and your fz becomes t plus z dz dA, which is nothing but the sigma zz plus, it's a very complicated expression, epsilon plus dou sigma zz by dou theta eta Ez plus some terms for E theta and another set of terms for ER. Whereas here you actually end up with sigma zz plus 2 sigma zz by dou z delta z by 2 plus times Ez, I think, plus tau rz plus dou tau rz by dou z into delta z by 2 times ER and another term for E theta. This whole multiplied by dA. So when we compare the integration that we get through the no assumption versus strong assumption, the deviation that we see, suppose f of plus z plus f of, I think for the z1 they come out to be same, but the forces for, say, r and theta, so this is no assumption minus the same bracket for strong assumption. This is of the small order, small o of delta v, which means that the term for no assumption is same as term for strong assumption plus some term which is less than, say, or which vanishes rapidly, which goes to 0 as delta v goes to 0. Okay.
Yes, sir.
So we have this third option for that. So which the third option essentially says the same thing, that in case of no assumption there will be a variation of traction over the planes, but when you integrate that variation of traction with respect to the area of the plane, we see that this overall term has an or is a small o of delta v term, which means that as delta v goes to 0, small o of delta v upon delta v goes to 0. Okay, the fifth problem, again a true or false statement. Epsilon is equal to half grad u plus grad u transpose can be applied for cylindrical coordinate system as also. So
True.
true, right? This is a simple tensor equation. So epsilon is half of grad of u plus grad of u transpose. And if you want, you can then confine it into a coordinate system, say E1, E2, E3. So you write the matrix forms for both sides in the same coordinate system. So you can write it for, say, Cartesian coordinate system, and you can also write a similar equation for the cylindrical coordinate system. So this is tensor equation, which means that it is independent of coordinate system. And if you want to write it in a coordinate system, we write it as we are showing ER, E theta, EZ. It's nothing but okay. You can make up a different coordinate system if you want, and again apply this to that, like the spherical coordinate system.
Sir, is there something like that? Can we apply gradient to a vector? Actually, if you see, if you apply gradient to a potential energy, you will get electric, if it is electric potential energy, you will get electric field vector.
Sorry, can you
Does
speak
it
up?
get? So, is there anything like applying gradient or the gradient of some scalar which gives an vector, like potential and gradient of potential energy gives an that
Hmm.
vector with respect to the potential energy. Is there anything related the gradient of some force here u is in a vector?
Hmm.
Is there anything like that in a real life, like if you see potential energy and electric field vector?
Hmm.
Is there anything we can relate anything for this gradient of vector?
Okay.
Because I am seeing this is the first time and I didn't see anything like gradient of some vector. I have seen gradient of some scalar
Hmm.
potential and gradient of potential. First time I
Okay.
am seeing this gradient you are applying to an vector.
So similar sort of equations also arise in fluids. So basically, in a when you have like a continuum, like you have in this case, you and that continuum is free to move across, say, multiple dimensions, say 2 or 3 dimensions, then you have then you have in that case you would end up with a gradient of a vector kind of scenario. A similar, like you have here strain, right? Similar stress strain also arises up in the case of fluid mechanics. So that is one example where I could say that you do see a gradient of a vector.
Okay, sir. We learned that in fluid mechanics.
But I think
We can
once
see
you'll start getting used to it once you.
okay, sir.
Yeah. Problem 6. To solve a deformation problem in cylindrical coordinate system, we require. So what of the following things do we require? Do we require stress equilibrium equations? So we do require, right? We are using linear momentum balance, right? So we do require the stress equilibrium equations in the cylindrical coordinate system. So okay, before we go and try to solve this problem for a cylindrical coordinate system, let us think in terms of Cartesian coordinate system, right? For Cartesian coordinate system, if you remember, if you have a problem, a body, say suppose it clamped like this and some force is applied, then we can solve this deformation problem if boundary conditions are given, which means where displacement is say constrained or force is applied. Secondly, you need the linear momentum balance and angular momentum balance equations, right? So these equations help you relate change of the derivatives of stress components with respect to your volumetric body forces and accelerations. Thirdly, you need a strain displacement relation. So a strain displacement relation is required to calculate strain in terms of say displacement gradient, and finally you need a stress strain relation. So you need to have boundary conditions. Then you have linear momentum and angular momentum balance, which give you say stress equations in terms of stress and equations in terms of stress and say the displacement. If you remember, you have a term u double dot on the right hand side, an acceleration term on the right hand side for these equations, and a derivative of say dou sigma ij by dou x, something like that. A derivative of stress on the left hand side. Then you sorry. Does anyone want to speak something? I'm not able to hear clearly.
No, sir. No, sir.
Okay, 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 good. The stress strain relations are important because then you can write say the sigma ij in terms of epsilon kl, sigma ij as a function of epsilon kl, and then the strain displacement relations are important because you can write epsilon kl in terms of uk and ul, right? So you have this equation, then you use these two to substitute here to essentially end up with an equation only in u, only in displacement terms. So all four equations are required. All four equations were required in case of Cartesian coordinate system. Similarly, you can similarly understand that you have your stress equilibrium equations giving you a relation between stress and displacement in the cylindrical system, which is say which is something like dou sigma r by dou r plus 1 by r dou tau r theta by dou theta plus dou tau r z by dou z plus sigma r minus sigma theta theta upon r plus rho pr is equal to rho ar. Ar is nothing but tau square by t square of u. Right. So we have this equation. Then the next one we have is relating sigma with respect to epsilon. Sigma with respect to epsilon. We substitute it here, and another equation that we use is epsilon in terms of u. That is then substituted here. So again, these three equations are definitely required, but this problem is still not solvable because it would not give you unique solutions. You only get unique solutions when boundary conditions are provided. So essentially, we are using stress equilibrium equation, stress strain relation, strain displacement relation, as well as boundary conditions. So all four are needed to uniquely solve any problem in any coordinate system. Okay.
Yes.
Problem number 7. For isotropic materials, stress equilibrium equation in terms of stress components has same form in both. Okay, I think we have to select which of this is the correct one. So the first option, and we are given that our material is isotropic. Yes.
False.
So the first one is not true, is it?
Yes, sir. Yes.
So the second option is components of strain matrix have the same mathematical form in both cylindrical and Cartesian coordinate system. This is also false. So if you want say epsilon xx, that is dou ux by dou x, whereas if you want say something like epsilon rr, that is epsilon rr is dou u by dou r. I think I took the wrong example, but epsilon yy is say dou uy by dou y, whereas epsilon theta theta would be 1 by r dou u theta by dou theta plus ur by r. So the form is say different from this one, whereas for the Cartesian coordinate system, x, y, z are independent and always fixed directions. For the cylindrical coordinate system, r and theta direction, which is e and er and e theta basis vector depend on theta. They are independent of r and z, whereas ez is always constant. It's independent of all r, theta, and z. So, which is why you end up with different forms here and here. The third option is stress strain relation in all coordinate system has the same mathematical form. Is this true?
True. True.
Correct. So for isotropic materials, I'll just digress a bit. For isotropic material, the directions do not matter. So long as suppose you choose a basis n1, n2, n3 which forms a right-handed basis, then you can write epsilon 1 is 1 by e times 1 minus mu sigma 2 minus sigma 3 and like this is the sort of laws we'll get up. So long as n1, n2, n3 form right-handed basis, we
Sir,
all
I think it should be sigma 2 plus sigma 3.
oh, apologies, thank you for pointing that out. Yeah. So the stress strain relation in all coordinate systems for isotropic materials has the same mathematical form provided the said coordinate systems are, like by coordinate systems we mean right-handed basis. Okay. Now we have some. Okay, we have to solve a numerical problem for questions 8 to question 10. We are given the deformation of the body. So UR is 0.01 R plus RZ, U theta is 0.02 theta plus RZ, and UZ is 0.01 R plus RZ. this is the displacement field in the body. So suppose this is our body. Wait. I'm just it can be still applied to any body, but I'm just purposefully writing it as a cylindrical body. So this is suppose your Z. This is your theta. So this is your point R theta Z. Okay. R can be here also. So not necessary that it has to be on the end. And we are given the displacement fields. Then we are asked hoop strain for the our deformation. So hoop strain, if you remember, so suppose this is the side axis. Hoop strain deals with after deformation. Suppose this has gone to this particular. So the hoop strain is a tangential strain, so to speak. So hoop strain epsilon theta theta is nothing but 1 by r times dou u theta by dou theta plus ur. Okay. Now this is u theta is nothing but 0.02 theta plus rz. Therefore, dou u theta by dou theta would be 0.02 and dou ur by r would be nothing but 0.01 times 1 plus z. So if, okay. So therefore we end up with 1 by r 0.02 plus ur by r, which is nothing but 0.01 times 1 plus z. Okay. Which of the options? I think the last option, right? This is the hoop strain. So you guys were able to understand the significance of this term, right? ur by r. So dou u theta by dou theta is relatively straightforward. Like this is say u theta and variation of this theta with respect to a small theta. Variation in u theta with respect to small theta. So this term is straightforward, but you are able to understand this term, right? ur by r.
Yes, sir. Yes, sir.
Yeah. So this term, if you remember, comes from suppose radius increases from r to r plus ur and all other components are held constant, u theta and uz. Then what we have is a increase in the circumference, right? Which in turn means that the hoop strain is non-zero. From there we obtain ur by r. What can we infer from the given displacement? So the problem 9 asks which of the options we can infer to be true. Okay, so we are simply being told u theta and uz, right? Correct. We are not being told the relation between sigma and u. Correct. Sorry, sigma and epsilon. From u theta uz we can calculate epsilon, but we do not know the relation between strain epsilon and stress sigma. Therefore, we cannot say anything about the material property. So we cannot say whether the material is either orthotropic or isotropic, right? And
Yes, sir. Yes.
and one more thing, the ur, u theta, and uz are already given, which means that they are your base independent parameters. These three form your base independent fields. These are the independent fields, and they in turn lead to 6 dependent strain components whose dependency is formalized using the strain compatibility conditions, right? So if we are given any displacement field, we do not need to worry about the strain compatibility conditions, right? We have discussed this, I think, in week 5.
Yes, yes, yes. This will definitely satisfy
Correct. So if,
the other things.
yes, if displacement is given, then strain will always satisfy. Strain will satisfy the strain compatibility equation. Okay. Right. So we can't infer anything. So none of these three options can be inferred. The final problem for today, epsilon rz for the above deformation will be. If you remember, epsilon rz is nothing but half of dou ur by dou z plus dou uz by dou r. Correct. And if we go back to our,
But there will be no
sorry,
is there off for that condition?
so this is epsilon rz, right? We are being asked epsilon rz, not gamma rz, right? You remember this, right?
Okay. Okay. Ah, yes, yes.
So grad u would, I think, give you something like dou r dou ur by dou z. Grad u transpose should give you dou uz by dou r, or perhaps vice versa. I think, yeah, I think this is correct. Or maybe the other way around. It doesn't matter because addition would be commutative. So it would still end up to half of dou ur by dou z plus dou uz by dou r. So we'll first calculate
Yeah,
those.
actually, dou u z by dou r plus dou u r by dou z. I think so. Yeah, grad u gives you dou u z by dou r, and grad u transpose gives us dou u r by dou z.
Hmm. No, I think the row is okay. Maybe I've gotten it wrong. Anyways, the epsilon rz would be symmetric, half of the symmetric sum, right?
Yes,
So,
yes,
so
yes.
you have dou ur. Okay, we'll look at dou ur by dou z, which is nothing but 0.01 r plus 0.01 r plus 0.01 r z. 0.01 r won't be 0.01 r does not depend on z, whereas 0.01 r z depends on z. So your derivative is nothing but 0.01 r. And similarly, if you do dou uz by dou r, again you have 0.01 plus, oh, did I make a mistake? No, right?
No, sir. Sir, 001 plus 001. I think. Dou u z by dou r.
Oh, sorry.
Yes, sir. Yes, sir. Right. Right.
Okay, right. I think I made a mistake in this equation. Writing down this equation, this probably was z plus rz, because yeah, that was z plus rz. I'm sorry. This should be z. I'm sorry about this. So we would end up with this answer. It doesn't matter, but it's not in the options. I made a mistake. Sorry. Okay. So uz is actually 0.01 z plus rz. Therefore, dou uz by dou r is nothing but 0.01 z. Therefore, dou ur by dou z plus dou uz by dou r is nothing but 0.01 times r plus z. We take a half of that, so 0.01 will go to 0.005 times r plus z. So epsilon rz is 0.005 times r plus z. Okay. Sorry for the confusion in the displacement field. Yeah. So do you have any questions from this week's content?
No, sir.
No, sir? Okay. Okay then. Thank you for attending this week's session. We'll be again meeting next week, next Tuesday at the same time, 7 to 8 p.m. on the same Google Meet link to cover week 8 content. Thank you.